start recording. Perfect. All right, so where were we? That's not the right course. So we were talking about the von Neumann CA, right? And we were at a point where, let me get back where we were. While crossing, right? So remember, let me zoom in a little bit, or that's fine. Well, that's fine. Okay, remember, so we did this channel crossing component, which allowed us to like send signals in and get them out wherever we want. And we showed that using this, along with a few other elements like the periodic pulsars and so on, we're able to code essentially inside the von Neumann cellular automaton a finite state automaton. Okay, so a small kind of computer, let's say. Okay, so we'll go in more details about what is a finite state automaton today. But let's just finish what we started last time. So last time, the last thing I showed you was this one. And this, I claim that, well, let me check because I think people are complaining about the live stream. Yeah, perfect. So this thing we showed, okay, just for one input, but is a proof of concept of how can you implement this, a finite state machine, so this thing here, inside the von Neumann cellular automaton, okay? And we stopped there. So that's already pretty good. And today we're gonna end with this construction in von Neumann. So we're gonna explain the constructing arm and then end it there. And we're gonna start explaining a bit from scratch, going away from A-Live, what is a finite state automaton and what is a Turing machine in a bit more detail. Okay, so this is not strictly A-Live, what we'll do today. But I think it's very important because it's kind of one of the few theoretical results that we have in artificial life. So we'll be able to kind of prove that we'll be able to prove that you can have self-reproduction, okay, in a kind of rigorous way. And that will be kind of it will give us, let's say, a guideline when we are designing alive systems, okay? Okay, let me just answer here. There is a question about the YouTube stream. Can I answer? No. There was this link. All right. Okay, so the constructing arm. So essentially what we constructed here with this finite state automaton is this tape reader or the computing unit, the brain of our machine. But of course, if we want it to make it reproduce, we need to be able to construct another machine, okay? And we haven't said, we know how to do computation or to compute anything, but we don't know yet how to construct things, right? So for example, I give you a computer, okay, a computer can do all sorts of computations, but if the computer is to self-reproduce, I mean, you have to give him a robotic arm so that it's able to assemble the components, okay? So that's exactly what we will look at today. So the tape reader is the finite state automaton. And what is the constructing arm? So we'll do a very simple constructing arm, okay? So it needs to be able to extend, right? If we want to construct something far away. It needs to be able to build new things, of course. And then it also needs to be able to retract because, okay, once we have constructed our thing, we want to remove the constructing arm and leave it at that, okay? So intuitively, okay, we know how the constructing arm will work. It will have both special transmission and ordinary transmissions. And we'll kind of use those to both construct new states using the sensitized state, and then use the special ones to destroy states whenever needed, okay? And the constructing arm is very, very simple, actually. So it is composed of this constructing head, okay, which is just 3 states. So you have 2 special transmission going to the right, and 1 ordinary transmission pointed at the special transmission one, okay? And so here by O and O, I just mean the input, the ordinary inputs and the special inputs. So they can get inputs from 2 directions at once, okay? So as you can see, using this head, we can plug some wires in 2 different ways, either horizontally or vertically, okay? So in principle, we could have a head, which, I mean, the head can be attached both to horizontal wires and vertical wires, okay? So far, so good. So with this design, we'll see that we can grow up and to the right and retract, well, down and to the left, okay? So before continuing on explaining you how does this thing actually work, we will just, instead of using like the complicated sequence of zeros and ones to denote the states, we'll use this simpler notation here, okay? So when I say send down arrow as an input, it just means send the sequence of excitations that encode the down arrow, okay? Remember last time with the sensitized state, each arrow has a different sequence of excitations, okay? So we'll use these symbols here, and C means send the sequence of excitations that makes a confluent state, okay? So for instance, the east-directed ordinary transmission means the sequence of excitation 1, 0, 0, 0, 0, okay? So now we can see. So first, let's see how do we advance the arm. So how do we grow the arm? Okay. So here I explain how to do it. So first, you send this sequence of inputs into the S, so into the special inputs, which will okay. We'll see afterwards what it does, and then you send this sequence here into O, and we'll see that this works. Okay. So here I have the example. So let's see. So first we send down special, then left special, then just a single one, and then right special. So this will start here. So we put a down special here, then a left special here, then we destroy it with a single pulse, and then we replace it with a right ordinary. Okay, so let's have a look. All right, here we put the down special, then we send a left special. Okay, so now we're pointed at the other bit of arm. So now we can destroy it with a single pulse, right? And then we replace it by a left ordinary arrow, okay? And so now we have to do the same thing with the ordinary arrows, right? We want to end up again with the constructor head. So here we're gonna destroy the red one, then point up, then destroy this one, and then create a new one that goes to the right, okay? So let's see it. So first destroy, then create an ordinary that points up, then destroy the red one, which is not in the correct direction, and then finish with the one in the correct direction, okay? So we went from this to this. As you can see, the head advanced by one square to the right, okay? And we're back in the starting position. So if you repeat this sequence of excitations, you can just advance the head to the right, all right? All good? Good. So, yes?
I don't understand how was the red destroyed? Because
so remember, whenever an ordinary transmission sends an excitation to a special one, it destroys it in one go, and vice versa.
okay.
So the blue ones can destroy only the red ones, whereas the red ones destroys everything except the red ones. Right? Yeah. So that's why we need our constructing head needs to be composed of half special and half ordinary, because we need to be able to destroy both special and ordinary in order to advance. Okay. Right. And so this is the horizontal advance, and then the vertical advance is much of the same. Okay. So here I show you the list of the sequence. There was a question, but let's just skip this one. So we start with this again, and we want to move up one bit. So we want to end up here, okay? So first, from going from A to B, you see we do the same thing. So first we extend one part of the arm to point at ourselves, and then we send further excitation to extend upwards, okay? So here, I suggest you try it at home, okay? If I send this input here in the O branch, in the ordinary branch, I send this input, this brings us to the intermediate state here. And then we have to send some other collection of inputs into the red branch to get back here, okay? And if you compare the start and end state, you see that we just advance the head by one block upwards, all right? So we have a way by sending the proper excitation in the red and blue wires to advance our head as we want anywhere, okay? But we need always to advance forward or to the right. And if you think about it, it's really easy to design a sequence of excitations that also retract from one bit, okay? So yeah, we know how to advance the constructor arm. How do we actually construct? And this is much of the same, okay? So to construct, what we will do is when you have the head in this position, like this, so you have the constructing arm, what we'll do is retract it by one step and leave behind what we want to construct, okay? So let's do the example here for constructing. So let's say we want to leave two confluent elements here. So we start from here, right? We send this sequence into the blue line. So what does this do? It first destroys the red one and replaces by a down one pointing red. Okay. Then we send this sequence into the red line, okay, which destroys the blue, replaces by a red, destroys the second blue, and replaces by an upward blue. So here what we did is essentially retract the arm by one bit. So you notice here we have again the construction head, but we are left with those undesired things. So now we have to get rid of those. Okay. So now we send this sequence into the blue. So what this does is it grows a blue line here and replace the red, the unwanted red one, by the state that we want. Okay. So here this delta just means send whatever state you want to construct there. Okay. In that case, we sent a confluent. So let's go through this sequence here. So one destroys the red one, then put a right ordinary transmission. Then one destroys the red one, then put a down ordinary transmission. Then one destroy this red one and put whatever state you want. Okay? Yeah. And now the same thing. Okay, we want to get rid of these and replace with the proper state that we want. We just send this sequence into S. So one destroy the blue one, then write ST, then one destroy the unwanted blue one, and then gamma for whichever state you want, okay? And we are left here, so we retracted the head by one bit to the left, leaving whatever two states we want, okay? And of course, this gamma could be just 0 if we just want to retract without leaving any states, okay? All good so far? So here we retreated horizontally, leaving gamma and delta, whatever states we want, in its place. So we can construct while retracting horizontally. Of course, we need also to be able to construct while retracting vertically. And here I won't detail the construction, but it's very similar. Okay, it's very easy to convince you. It's actually a good exercise to do that. Try and see. Start with a vertical head and try to see which sequence of excitations you need to send to retract it by one and leave two arbitrary states behind. Right? Okay. So if I give you just two cables that connect to a constructing arm, and I give you two buttons, one that sends excitation to the special wire, and one that sends excitation to the ordinary wire, you should be able, just by tapping these two buttons, to construct anything you want. Okay? So the way it works, it's kind of like this. Okay. Let me, full screen. It's worse. So here, what do you have? So here, this big block is just some coiled wire that contains a set of excitations. And here we have a constructing arm on the right. And you see, as the excitation go in the constructing arm, they contain the code essentially to construct this phrase here. Okay, this word, right? So this is the same thing. So if I give you two buttons, one for the ST, one for the OT, you should be able to tap the buttons in such a way that you construct anything that you want. In this way here. So you grow the arm to the top right, and then you retract while leaving behind what you want, then grow it back, then retract, grow back, then retract. Okay, as it's doing here. So it grows, then it retracts, leaving behind what it wants to construct. Okay? So this is a project idea, maybe more for computer science people. You could write a compiler, okay, So what it would do is that you give it in some format that you want a state of the von Neumann world, okay? So a machine in the von Neumann CA. And you design a compiler that translates that into the sequence of excitation you need to send in the special and the ordinary wire such that it constructs it. Just a project idea if somebody is interested, okay? And then what we can do once you have this compiler, I can just hook it to my simulator of the von Neumann, and you can actually produce videos like this one, which construct whatever you want, whatever image you want in some sense, okay? So the takeaway here, oh God. The takeaway, sorry, yeah. So the key takeaway here, given the right sequence of excitations, we are able to convert it into any arbitrary configuration, okay? Are there any objections to that or any uncertainties why that might not be possible? You should be convinced that this is true, right? So by the way, so last time I raised a potential problem when I told you that you can build a pulsar for any sequence of series. So we had this problem that if you need million of inputs, you might not be able to kind of have enough space to synchronize them. And if you really want to know, the solution to that is just if you have a million input, you first put them on a parallel highway, and then you can extend this highway as much as you want with confluent elements such that they synchronize as you wish, right? Because the problem was that maybe you cannot synchronize two signals that begin super far away with the ones in the middle because they have a lot more more travel to do. But if you do a sufficiently high highway, you can synchronize just by putting more confluence in the signals that are in advance with respect to others. Okay, that's just a note for last time. So, okay, we have the constructing arm. We can construct anything we want. And so now you're starting to see how we'll build this self-replicator, okay? We just need a machine that is able to produce the correct sequence of excitation to build itself, right? Okay, so we need a final component, and we'll see later in the course why this is crucial, okay? Because right now we have the finite automaton, quote unquote, the processor of our computer, and we have the constructing arm, okay, so what will construct the new state. But we don't have any way to store the information, okay? So in a sense, we need a hard drive that contains the program to execute. Because, for example, in this example here, this is not very practical, right? Because the information stored to construct this word here is contained as excitations on a tape, right? So it's very volatile in a sense. So we need some way, some kind of tape, which is kind of hard drive, so something that contains information. And we'll see why you might say, okay, but maybe if you have a processor which is good enough, it can contain the information inside the processor itself. And today we'll see why that is not true, okay? But for now, let's accept that. So yeah, so we'll use a tape, okay? So I don't know how many of you are familiar with VCR or VHS cassettes. So raise your hand if you're familiar with what it is that, just to get a feeling of, okay, that's fine, yeah. So people are not as young as I thought. So yeah, so you have a cassette, so you have a tape that contains information which is written sequentially. And that's what we will use to store information, okay? So the last bit we need to describe fully our machine here. We have the constructor arm, we have the tape reader or the processor. We are left to describe the tape, okay? And this will be, again, relatively simple, okay? So that's what it looks like. So here we have the tape proper. It's just a line of states. And the tape uses a binary encoding, okay? So you can interpret when there is no state in a square, it means it's a 0. When there is a downward arrow, it means there is a 1, okay? So 0 will be the ground state, 1 will be the downward OT state. And then you need a tape reader, so something that can tell you whether there is a 1 or a 0 on the tape. And this is the two things on either side of the tape. So let's see how does it work, okay? Yeah, and additionally, we need a tape reader, but we also need a tape writer, okay? We need to be able to kind of store information on our tape. So we need to be able to write or erase the tape as well, okay? And that's what these 3 lines do, okay? So let's see first, how do we read, okay? So reading is very simple, okay? What you do is you send this sequence here, 1, 0, 1, 0, 1, into the ordinary wire here, okay? So what will happen when you send this? Okay, if there is a downward arrow, the sequence will just go through. So at R, you will receive 1, 0, 1, 0, 1, okay? If there is nothing, what will happen is quite interesting. So you will see that if there is nothing, this sequence of excitations, I don't have the table here, but believe me, encodes the downward arrow, okay? So the first 1, 0, 1, 0, this encodes the downward arrow, and then the last one is extra. So if there is nothing when you send this 1, 0, 1, 0, 1 into O, what it will do is create a downward arrow and propagate the last excitation, okay? So what R here will receive will be just a single excitation, okay? So now you know, if you look at what comes out of R, you know that you will get 1, 0, 1, 0, 1 if there is a downward arrow, and just a 1 if there is no downward arrow, okay? So let's see this in action. Oh, what is he doing? Yeah. So here, okay, just don't look at all the things around. This is just to store the excitations, okay? So here we have the tape reader. You see it's here. And here we have the tape like a receiver, okay? So you should focus here, what is received here, right? So first we send 1, 0, 1, 0, 1, okay? So here we want to read that there is nothing, okay? So let's see it. So as you send your excitation, tac, 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 it creates a downward arrow and it propagates the last excitation, okay? So here we read, we received 1 excitation, so we just read a 0, okay? And conversely, if there is an arrow, of course, I mean, everything goes through. And so you read a 1 whenever you notice that there is this thing. So the crucial thing to notice about this read operation is that it's destructive, okay? So we just read that there was a 0 on the tape, but in doing so, we changed it to a 1, okay? That's not ideal because, I mean, yeah, when you read your hard drive, you would like to be able to read some files without destroying them, okay? Here it's destructive, but that's fine, right? Because one thing you could do is just say, okay, if you see a 0, first erase it and then do whatever you're supposed to do when you see a 0. So that's not a limitation, okay? It's a bit annoying, but it's fine. Okay. So now we know how to read, okay? The other thing we know how to do is how to write a 0 or how to write a 1, and of course, how to advance and retreat the tape reader, okay? And this is very similar to the constructing arm. So if you look at the head of this tape reader, it's like the constructing arm, but it's inverted. So the OTs and STs are inverted. So you can use much of the same procedures to advance and retract it. It's kind of the same idea. But of course, the problem is that you have this receiver down there, okay? You need also to extend the receiver. Because of course you could say, but just start with a receiver which is extremely long, but the tape can be potentially infinite, right? The tape can extend infinitely long. So you need to be able to extend also this receiver cable if needed. Okay, and intuitively it's very simple, okay? If you look at this as a constructing arm, if you want to extend to the right, you first go down there, add an additional OT here for the receiver, then go back up, then advance the arm, okay? That's what you need to do, okay? So in practice, it's quite complicated, but let me just show you what it does. I mean, if you think about it, you can design it very easily, but it's a bunch of excitation. I mean, there's a lot of stuff to do. So let's see here. So here we have the constructing arm here, and I think I'm gonna show you how to advance it by 1 bit. Okay, let's see. So the first thing is to advance the receiver down there. So let's see it. So of course, to get to there, you need to make a path of ST that goes up to the receiver to be able to destroy the things that you need. Then you leave what you want to leave. And then now you destroy the extra red path. Okay, continues. Destroy the red one there and leave what we need to leave. Then back to the red one to destroy the unwanted blue ones. Okay. And now we're advancing the reading part. Okay. And this is just like the constructing arm. Okay, we first look at ourselves and then we go back to destroy the things that annoys us. And okay. Okay, perfect. So it's quite complicated, but it is doable. So you can, and of course here, so here we decide to advance the arm writing a 1 on the tape. You can do the exact same procedure, leaving a 0 behind. Okay, you just need to change one set of excitations. Okay, so this is very complicated, but what you will do if you were to build a computer inside the von Neumann CA is that you will prepare a pulsar that whenever you give it a single excitation in, it will produce the advanced tape. Then a pulsar that retracts the tape, a pulsar that reads the tape, etc., etc. So you can control everything just with a single excitation if you have the right pulsar behind. Okay? Any questions so far?
Is this also destructive because it passed through the tape?
Right. So the question is it also destructive? And the answer is yes, but you can choose what to leave behind. Okay. So if you just read the tape, you know if there is a 0 or 1 there, if there was a 0 or a 1 there. And so when you advance the tape, you can choose to leave whatever you read before. So you can make it non-destructive. It's a lot of extra steps, but as long as you can undo what you destroyed, it's fine. Okay, so now we are done. We have our tape that works well. We can read from it, we can write on it, etc., etc. And of course, yeah, as I said, it's very convoluted how this tape works. There are probably better designs for tape in the von Neumann CA, but that's good enough. We don't need it to be efficient or whatever. If we know that it can work, that's good enough for us. Okay. So the full machine is this thing. And yeah, so here was the end of the course from last time. So what we'll see today is that a finite automaton acting on an infinite tape is actually the definition of a Turing machine. Okay. So okay, let me skip that. And so here I want to show you, just to finish this part. So this, I don't know, yeah, it's clear. Okay, so this is an actual implementation of a self-replicator. Okay, so this in principle is something that is able to self-replicate. Okay, so let me show you. It's very complicated, right? But you can recognize some parts. So if you look here, you see this, this is precisely the constructing arm. Okay, this bit here. So this is from where it will go and construct the stuff. And here you can note that this is the reading part, and here you have the tape composed of downwards arrow. Okay, so this in principle, the way it works is that you send a single excitation here, it turns on the machine, and it will read what's on the tape and execute whatever the tape tells him to do. Okay, so this part here on the left is actually the computing part, and this full part here on the right is just some redirections, wire crossing or whatever, a very compact wire crossing. And so unfortunately, so the guy who made this machine is called William Buckley, and he posted it on the internet. And so I said, okay, I'll put it in my program and try to simulate it. And unfortunately, it is bugged. Okay, so let me show you what happens when you turn it on. So you can see here, there is a single excitation traveling inside. This is normal. This is kind of a NOT gate or something. So here the excitation goes through, okay. It goes through the arm, it reads the arm, okay. It produces another excitation. Now it starts to do some computation, and then, okay, it floods with excitations here, and this is not normal, okay? So I wrote an email to William, and I asked him, okay, is this a bug or is my implementation kind of wrong or something? And he said, okay, that's actually a bug. We found the bug, it's right here. We fixed this bug, but it still doesn't work, okay? So the problem that it has is that it advances the tape, but it kind of do it wrongly, so it does not end up with the advanced tape reader, so it fails. And so right now, with William, we are trying to see if we're able to fix it. I mean, he's mostly doing all the work because I don't understand these things very well. But yeah, so I'll let you know if we're able to fix it and kind of simulate it. But even if we do, okay, we said that we just want to prove self-replication, not actually do it efficiently. So people have computed it. So here, William actually computed the actual tape you need for the self-replication. It's something like 100,000 cells long, okay? And then you can estimate the number of steps you need for the replication. It's like, okay, 10 to the, I don't know, 20 or something. So it cannot happen really in our lifetimes, except if you do some incredible optimization. But okay, for the people did other cellular automata, which are kind of simpler than von Neumann by adding a few states. Like last time there was the question of why not add the not state, for example. Yeah, this simplifies things a lot. And so in these simpler versions of the von Neumann CA, you have actual implementation that can run. But they are very rare. I mean, it's very rare to find them. But yeah, this is the fruit of all your work. You have just the tape reader, the constructing arm, and this full thing is the tape reader, which is quite complicated, of course. But yeah.
So why is the pulse only 0 or 1? I mean,
The what?
pulse.
The pulse?
It can be any number, and you know what to construct or what to do.
So what do you mean? Which
I mean,
pulse?
The yellow pulses that we see.
Yes.
Now it's just 1 bit.
Yes.
But it can be any number.
Yeah, of course. So the thing is that just to keep things simple, every time you need like some complicated series of excitation, you just put a pulsar that generates this, so that you can activate with a single pulse. So when you see this, so here you see that when you read when you read the tape and you get a 1, okay, here you have the output. I just read a 1, so the excitation is on a different cable according to what you read.
My question is design choice. Like,
yeah,
why don't we choose the pulse to encode any numbers, like up to?
you mean inside the design of the cellular automaton itself? Yeah, you could, of course. Yeah. So if you choose a pulse that can encode any number, but then the thing is that you have to define any state, how it acts according to the different numbers, right? Most states will act the same, but you could do this, of course. Yeah, this would make for sure things more compact. But yeah, so I think with any pulse, probably. I think von Neumann really wanted to like have a cellular automaton which is as simple as possible, in some sense, proving that you don't need complex stuff to make a computer. But there are, of course, many ways to simplify it. Yeah. Other questions before we start on the Turing machines? Okay. So Turing machines. Actually, no self-reproduction today. It will be for next time. So you can join the Slido here. Let me make a screenshot of it as well. Whoops, no. That's annoying. Up. And let me put it here. Perfect. Okay. So this is the Slido code if you want to join. And okay, today the reference is some theory of computation book from Michael Sipser. It's very good. I recommend it if you're interested in these things. And as I said, okay, today it's not really artificial life, but it's very important as preparation for what we'll need. Okay, it's mostly theoretical today, no pretty images, unfortunately. But all right. So first question that I have on the Slido, actually, if you can answer just to get an idea. So the question is, do you know what is a Turing machine or not? So let me see here. Yeah. Okay. Let's wait a bit more. All right. So it's about. Okay, that's good. Okay, so for some people this will be boring. Maybe you will still learn something, but it's important that everybody's on the same page with this stuff. Whoops. Just a second. Okay, yeah. 60% know, the rest kind of don't know, and the others, we don't really know what they think. But okay, so good. So what is the reason for studying these Turing machines from the point of view of A life in particular? Okay, so one of the defining properties for some people, not necessarily, but it's certainly a certain property of life is self-reproduction. Okay, it kind of feels like if you don't have self-reproduction or at least some kind of duplication, it feels hard to feel like it's life. Okay, and to have all these other properties like evolution, complexification, etc. Okay, and as I said, I think I said it in every course. This paradox of machine self-reproduction that was kind of prevalent for some people before von Neumann is that okay, to reproduce the machine must contain a blueprint of itself. If the copy of the machine also must be able to reproduce, otherwise it's not a copy. It also needs a blueprint of itself. But then this means that the initial machines need a blueprint for the blueprint so that it can make a new blueprint for the new machine. But then you continue and so on and so on. Then you need a blueprint for the blueprint in the copy. So it means that the initial machine needs a blueprint of a blueprint of the blueprint. And okay, this is not very clear, but I think this picture is extremely clear of what we mean. Okay, so this is the initial machine with its blueprint. And on the blueprint, you should like take this image and put it on the blueprint, right? But if you do this, you include the image of the blueprint. And so you need the blueprint of the blueprint, etc. So this blueprint is not possible to do, right? Because you need infinite detail to have all the chains of blueprints. And thus, you cannot have self-reproducing machines. And then you will say, of course, yeah, that's stupid because cells, for example, cells are self-reproducing machines. So there should be no problem. And some people thought that the solution to this was not that self-reproduction is actually possible, just that a machine and a living thing is kind of fundamentally different. There is some special thing about the living thing. And that's why machine cannot reproduce and living thing can. Okay, of course, this is wrong, as we'll show today. So we'll show how explicitly can a machine reproduce. Actually, this will be the next course's subject. Today we'll set the groundwork to be able to show that. Okay, so let's start from something you are familiar with, the finite automaton. The finite automaton. So as we have said, it's essentially a machine with a finite number of states and a predetermined transitions between states. Okay, this is the picture. So you have two states, and then you have arrows that tells you how to transition from state to state. And the way you choose which transition you employ is by the input that you read. Okay, so if you want to define it a bit more mathematically, a finite automaton is described by 5 objects. Okay, these 5 objects here. So first you have a set of possible states, which will denote QIs. Okay, you have an initial state Q0, which is just the state in which the machine starts in. You have an alphabet, okay, which is just a set of symbols or words or whatever, or images, which is the possible inputs that can the state machine receive. And then you have the transition function. Okay, the transition functions tells you that given a specific state and a specific input, that's the new state the machine will be in. Okay, and in addition to that, you have this A, which is a subset of the total number of states. These are special states called accept states. Okay. So the way the machine works is very simple. Okay, we feed him a string of these symbols, character by character, and the automaton just processes the symbols one by one. So the input is received one by one in this string of inputs. And it processes them. How does it process them? Well, with the transition function. Okay, it starts from Q0, look at the first input, changes its state, look at the second input, change the state, third input, change the state, and so on and so forth. Okay? And what happens is that you feed him all the string, okay? You make him look at all the string of inputs. And once you fed him the last bit, the last symbol, you look in which state the machine is. If it is in a state which is an accepting state, then we say that the string is accepted. Otherwise, the string is refused. Okay? So that's how it works. So in this definition of the automaton, it can only accept or refuse an input. Okay? It cannot do more fancy stuff like generate an input or something like that. It can just binary. Okay, we'll see that's not too important. And so this finite automaton, its proper name is Deterministic Finite Automaton, because there are also non-deterministic versions, which we also name DFA. Okay. So just to remind you, so in the von Neumann CA, we also made a finite automaton, but it was more expressive, right? Because for each input, it could output something, if you remember. Okay. So this is the example here. So the finite automaton we define doesn't have these red arrows, but you can just add them. Okay, so this is kind of the same thing. A finite automaton that also has outputs is just a finite automaton where you look for each transition, and to each transition you assign an output. Okay, so for example, if you locked and you employ you take this transition here when you receive a coin, then you consider this as outputting go. Okay, so this is just something you can add to the automaton. My computer is turning off. 1 second. Oh. Oh, I forgot the pause, right? Oh, no, it's right on time. Perfect. Okay, so the one we define here is much simpler, just accept or refuse, but this is not a limitation. Okay, if you want to treat it as outputting some special thing, just look at which transition it employs each time and consider this as output. Okay, so that's what I say here. And the precise name for when the output can be anything other than accept or refuse is a finite state transducer, but it doesn't matter. Okay. So to study these DFAs, we will focus on yes or no questions, and we'll see they are sufficient to see why this finite state automaton is not powerful enough. Okay, it's not a computer, let's say. Yeah. Okay, so let me just define what a language is, and then we'll do the 15-minute break. So we want to test, really what we want to show is that why we need a Turing machine. Okay, so we want essentially a test to gauge how powerful a machine is. And here by power, I don't mean how fast it can compute stuff or whatever. It just really mean by what problems can it solve, okay? I don't care if it solve it in exponential time or exponential of exponential time. I just care if there is a solution, which is possible, okay? So the task we will use to gauge this power, okay, will be just to recognize some set of strings. Okay, so we'll define a language. Okay, a language is very simple. It's just a set of strings, so a collection of strings. By strings, I just mean a sentence. Okay, and each of these strings, is a finite set of symbols. Okay, so some examples are very simple. So if we consider the set of symbols 0 or 1, these are the strings. So it's any sequence of zeros or ones, and these are languages. Okay, so here we have a language containing these strings here. Here we have another language. So this is the language that contains the strings that have exactly, the strings that contain only ones, okay? Here we have a language which is much more complicated, okay? This is a language which contains the strings which are a program that creates a life in Python. This is also allowed, okay? The only restriction is that your string should be of finite length. That's it. Okay, and in that case, the alphabet that we have is just all the characters that you can use to code in Python. Okay, then you can have also more complicated languages like this one. So here it contains all the strings that are accepted when you feed it into M, where M is a DFA. Okay, so really the languages can be defined whatever way you want. It's just a set of strings. Each string should be finite. last remark, the language doesn't have to be finite, right? So for example, this language here has a countable infinity of elements, but it's still a language, okay? And okay, I think it's good to make the pause here, and then we'll look at the power of the DFAs. Okay, so let's reconvene at 15:15. Okay, let's restart. So yeah, so we defined these languages, which are just sets of strings. And now we want to see how we can use them to gauge how powerful some computing paradigm is. So in this case, how powerful the DFAs are, okay? So to do this, we'll say that we'll ask ourselves what class of languages it can recognize, okay? So yeah, this will tell us how powerful it is. So if another machine that we construct can recognize more languages, we'll say that it's more powerful than the previous one, okay? So what does it mean to recognize a language, first of all, okay? So for a DFA, it's very simple, okay? The DFA recognizes the languages if it accepts exactly the strings of the language and none other, okay? So this is equivalent to say if it accepts a language L, if the language L can be equivalently written as W, W is accepted by M, okay? So just what this means is just that a DFA recognizes language L if we have this equivalence. So whenever the DFA accepts a string, this is equivalent to the string is in the language, okay? This implies that if you give it a string which is not in the language, it will refuse, okay? So we'll make some examples to clarify that, but yeah. So the class of languages, that's just a definition. The class of languages which can be recognized by a DFA, we'll call them the regular languages, okay? So if I say, let L a regular language, it just means that you can construct a finite automaton that recognizes this language, okay? So let's look at some examples. So the first language is this one. It's all the strings. So let's first determine the alphabet. So the alphabet is just zeros and ones, okay? So we have these first languages, which is all the strings that contain an even number of zeros, okay? And the question is this language recognizable by a DFA, okay? So think about it for 10 seconds. Do you think you can build a DFA that recognizes language? Then we'll have actual questions. So here, just the easiest way to think about it is really with this image of the states that flip, okay? So in that case, the answer is yes. And the DFA that recognizes language is the following, okay? So let me explain a bit the conventions here. So Q0 is the starting state, and the states which are red are refusing state, whereas the states which are green are accept states, okay? And then the transition is according to what we read, okay? So how does this DFA works, okay? What we want it to do is to end up in this green state whenever there is an even number of zeros in the string that we give it, okay? So essentially we need to count the number of zeros modulo 2. So that's exactly what we do. So we start here. If we get a 0, then we have an odd number of zeros. So we go to the refusing state and we stay there so long as we see only ones. Whenever we see another 0, okay, we're back at an even number of zeros, so we're in accepting state. And if we see ones, we stay here, okay? So it's clear that this will accept exactly when you have an even number of zeros. Okay, is that clear? Perfect. So let's see another example. So let's see this language here. It's all the string that contain 001 as a substring. So it's all the strings that contain this sequence, 001, okay? And this language is also recognizable by a DFA. And this is one example of a machine that does this, okay? So how does it work? So we start here, a refusing state, okay? And what the goal is to get to this 001, okay? So if we get to these states, it means we have seen this substring. And so when we're here, we stay here until the end of the string, such that we accept the string. Okay. So how do we get here? Well, it's fairly simple. Okay. So if you want to check if 001 is in the string, how do you check that? Well, you check that there is a 0, and then another 0, and then a 1. Okay. If at any point you don't see what you want to see, you go back to the start. Okay. A very simple design, and you can convince yourself quite easily that this works, right? If the only way that this will end up in this green thing is if you have 001 as a substring of the thing that you feed it. Okay. So one important note is that the DFA is obliged to go to the end of the input. Okay. Here we could say, okay, whenever we arrive here, we can just stop. We don't need to see any more string. We know that the answer is yes. You're not allowed to do that in the way the DFA works. Okay. You have to stay here until the end of the input, and this is just done by putting a transition that sends only in this state. All right. Yes, a question.
Maybe a second question, but why, if you have two zeros, does it go back to the start? Because you could have like 3 zeros and then a 1. And that would, I mean, it depends how you define substring. But
so the substring is really, you need to have 001 somewhere.
Because in that case,
I see. You're right. Okay. So yes, that's true. Okay. So my machine is wrong, right? So here with the 0, you should go back here, right?
No, you go back to itself.
To itself. Yeah. To itself. Yeah. Exactly. Okay. Good. Yeah. Good point. Yeah. Yeah. So my machine is wrong. Yeah. Yeah. So this 00, you should go back to itself. Otherwise, you don't recognize the language that I claimed it was recognizing. Okay. But very good. Very good. I missed that. Yeah. Okay. So question 1. So this you can look at the Slido. What language does the following DFA recognizes? So I may have made a mistake here also, but okay, yeah. I don't know if you can see the answer. Okay, we have a few answers coming in. Okay. All right, so let's see the results. So wisdom of the crowds hold here. So if I didn't do any mistake in the construction.
But it was multiple choice.
Yeah.
Right.
So okay, so the answer is the strings that start and end with the same character, in that case 0 or 1. Okay, so how can we tell? So first of all, if you get an empty string, okay, you could argue that it ends and starts with the same character. Okay, this is some semantics. But the empty string refuses, okay, because we end up here. And afterwards, what happened? Okay, according to the first character that we see, 0 or 1, we go either onto the left or the right side. So if we see a 0, we remain green as long as the last character we saw was a 0 also, okay? As soon as we see a 1, we go into refusal state. But if we again see a 0, we go back here. So as long as we end on 0, we'll be fine, okay? So this branch detects things that start and end with 0, and it's the same here with 1, okay? So this part, accepts the thing that start and end with 1. So overall, you detect things that start and end with the same character. Okay, other questions, which is a bit harder. Let me just check. Yeah, hide live results. Perfect. Right, so the other question is the following. I have this language here. And the question is it a regular language? Just to make it precise, so what I mean by 0 to the n, 1 to the n, I mean the strings which have n zeros and then n times the number 0 and then n times the number 1. And they can have up to 2024 zeros and ones. Okay, so the question is this a regular language? Maybe you can infer the result looking at question 3. But okay. Most people seem to agree that it is. So is there somebody that wants to give an idea of how you would build such a machine? Any ideas? Don't need to detail it exactly, but just abstractly, how would you build that?
Yeah, 2024 zeros, like states counting zeros.
Right.
After that, and from each state counting 0, we have a branch that counts less ones.
Okay. Okay. Good. Yeah. So that's a good idea. So the answer is yeah. The answer is indeed yes. Okay. It is a regular language, and actually, one thing that you can convince yourself of, it's not so easy with the tools that we have, is that any language that has a finite number of string is actually a regular language. Okay, so the answer that was given here, it's actually a smarter way to do this. Okay, it's the so-called elegant resolution. So the way you do this is, as Hassan said, you have a string of states, okay, all connected to each other by a transition as we see zeros, okay, that counts the number of zeros. For example, if we see three zeros, we get to the state I have seen 3 zeros, okay? And so you have a branch of 2024 such states, and as soon as you see a 1, you branch to another string of counting ones, okay? So what you do to accept or refuse is that all the 0 states are refusing, okay? Then once, if you are, let's say we are on the I have seen 5 zeros, okay, and you see a 1, you branch to another branch that has exactly 5 refusing state with 4, and the 5th one is the accepting state, okay? So that way, the only way to end up in this accepting state is to see 5 zeros, then branch to the 1, see 5 ones, and then end there, okay? So this is one way to do it. So here is the description of the solution, but okay, it's a bit more describable. But okay, the other thing I mentioned is that if a language is finite, has a finite number of strings, it is always recognizable. And here is a hint of how to prove that. So it is clear that we can build a DFA that recognizes any of the specific strings, right? I mean, we have seen that we can recognize a substring is just as easy to write a DFA that recognizes exactly one string. That's fine, okay? And then what you need to do essentially is simulate in parallel all these 2025 DFAs or 2024 with a big DFA, okay? And so the kind of tricky part is how do you simulate them in parallel, okay? But you can actually build such a parallel DFAs, and sometimes it's called a non-deterministic finite automaton because essentially it's branching in several branches at once, okay? And the way to do it at a really high level is very simple. It's that you have this big DFA, and it has a huge amount of states, and each of its states encode the states of all the parallel machines, okay? So the Q big contains the info of DFA1, DFA2, DFA3, etc. And if you use this huge big states, you can just look at what every machine wants to do in the next state and go to the corresponding big state. And what you do is if any of the underlying machines accept, then the big machine should also accept. Okay, it's not very clear, it's not very rigorous, but that's how you show that if you have a language which is finite, you just simulate in parallel all the DFAs that find each individual string, and so you can recognize the language. Yes? Question?
Why is this called non-deterministic?
So it's called non-deterministic because one way to see it is that you start with the first state and you have several arrows for the input 1.
No, we don't.
No, but the definition of the non-deterministic is like that. So in parallel, you go 2 ways. You see what I mean? So it's not non-deterministic in the sense that you have probabilities for each branch. It's that you take several branches at once. You're allowed to make several branches for each input. So in this case, when you see a 1, you're allowed to put 2024 branches for each of the underlying automata, and you compute them in parallel. So if you want more detail on this, you can look at the reference I gave. It's explained very well there. But okay, yeah, so you were right. And so the last questions, which is kind of obvious now. So is this a regular language? So exact same thing as before, but infinite number of strings. Okay. So I won't keep the suspense very long. People say no. The answer is no. The way to show it, I won't go through it because you need kind of more technology. But you can kind of convince yourself intuitively why it's not the case. Because to recognize this language, you need to count the number of zeros and then count the number of ones and see if they correspond. Okay. In the previous question, the way you did that is by putting one state corresponding to 1 0, 2 zeros, 3 zeros. Okay. So intuitively, whenever you want to store information in a DFA, you need to put an extra state that corresponds to this information. So here, intuitively, we cannot build a DFA because we want to be able to count arbitrarily big. So it means that we need an arbitrary amount of states. Okay. So this is one way to convince yourself. There is a way to prove it unequivocally, but you need some technology. So you can look again at the reference if you're interested. Okay. But okay, so the important thing here is that, okay, these finite automata are kind of powerful. They can recognize many languages, etc. But there are some simple languages like this one here, which they cannot recognize. Okay. And if I tell you, okay, write me a computer program that does this, that recognizes these languages, I think you can safely say that you will be able to write that. Okay. You might object that you say, okay, but if you give me a number which is n to the 10 to the 10 to the 10, then I'm not able to do it because I don't have enough memory. That's a valid concern. But given infinite memory, you would be able to code such a function. Okay. So this tells us that the DFAs are actually not powerful enough. Okay, we can define some computation scheme which is more powerful that would allow us to actually accept or recognize such a language. Okay. So here I will skip this part. So in this part here you can freely read it at home, but we look at the precise class of languages that can be recognized by DFAs. Okay. It turns out that you can characterize it very precisely. And if you've heard of regular expressions or regex in computers, the sets of languages that are generated by regular expressions are precisely the languages that can be recognized by DFAs. Okay, so you can read this at home if you want. I'm gonna skip it because it's not so useful. But just know that we can characterize exactly which languages can a DFA accept. So this is okay. So let's move to Turing machines, which what we wanted to do from the start. Okay. So we saw that DFAs are not powerful enough to recognize some languages that we know we could build a program to recognize. Okay, so in a sense, the DFA is not a good abstraction of what a computer can do. It's not powerful enough. Okay. And we have seen that intuitively, one way to make them more powerful is to be able to give them some memory, some place where they can actually write stuff down to remember, instead of having to use a state for each thing they want to remember. Okay? So that's exactly what we do. Okay? We give them a tape that contains some characters, and we give them a way to write and erase on this tape. Okay? Otherwise, they are precisely the same thing. Okay, the only difference is that now they have access to the tape. Okay, so this control part, so this is a sketch of what we call a Turing machine. We'll define more precisely. So the control here is a finite automaton, just the one that we mentioned before, with some outputs. Okay, and we give him some additional capabilities in that it can both read and write at the current selected location on the tape. Okay, and it can decide whether to move right or left. Okay, so now this should ring a bell. So what we did with the tape in the von Neumann CAs was precisely that, right? Okay, so the tape is just a one-dimensional strings of character, and crucially, it is infinite. Okay, you have arbitrary space to write down stuff. Okay, and to begin with, when we start our Turing machine, it should be completely empty, save for some finite piece of it. Okay, so we cannot start with infinite information on it. Okay, it always has an empty character, and the rest of the characters that we can give it are just free. Okay, you can write zeros and ones. You're allowed to add any character in the alphabet, whatever you want. Okay, and now the control. So before we had the accept and refuse state. Now, instead, we have a special state, which is the halt state. Because before, so essentially before, we knew automatically when the DFA will halt. It just halts when it finishes reading the string. But now, since it can access the tape and write stuff and go back and forward, we need a state that tells us whenever the machine is done, right? And this is the halt state. So when the control reaches the halt state, it just stops computing and we consider the computation as finished. Okay? And as well, if we work on decision problems, just like with the languages, we can have some special reject and accept, which are also halting states. All good? So this is the kind of abstract picture of what a Turing machine is. And so just using this abstract picture, let's see now if by granting him access to this extra tape, whether it can recognize this language that was problematic for the DFA. Okay. So the way we give it the input is now that we just write it on the tape, and it begins with the input on the tape. And then how does it do to recognize the thing? It's very intuitive. So first we handle the edge cases. Okay, let's say that you have an empty string or a string that starts with B or something like that. That's fine. So essentially what we do is we verify it is of the form A to the I and then B to the J. Okay. And this actually a finite automaton can do that. Okay, if you think about it, just a normal DFA can recognize strings of this kind. So here we don't need like any fancy stuff. We just read the tape and act with the finite automaton, and we see if it's of the form A to the I, B to the J. If it's not, we halt and reject. If it is, we continue and we try to see if there is the same number of A's and B's, right? And to do that, we just start on the beginning. We erase the first A. Then we go forward until the end of the string, and we erase the last B, okay? If we don't find any B before the end of the string, we just transition to the reject state. It means that there are more A's than B's. If we find a B, we erase the B, and then we go back to the beginning of the string, and then we repeat, okay? And so the only way we accept is whenever we erase a B and we go back and there is no A. This means that there was as many A's as B's, and so we can accept. Okay, and so you can see that this machine will work for arbitrary lengths of A and B's. It has no problem, simply because it does not need a state to know how many A's and B's there are. Right? It can just write a counter on the tape. Okay, so more explicitly, another solution would be to just scan the A's and you use another part of the tape just to put a mark. Each time you count an A, you put a mark on your tape. When you're done with the A's, you do the same thing with the B's, and then you check if the two counts are equal. So it's clear that it's possible with a Turing machine. So at least it's more powerful than a DFA. So that's good. But how powerful is it? Can we make it more powerful? That's what we will see. Okay, so the rigorous definition for people that want those. The Turing machine is a set of 7 elements, so slightly more than the DFA. So again, we have a set of possible states. These are the states inside the control, so the finite automaton. Sigma is the input alphabet. Okay, the input alphabet is just a series of symbols. And the blank symbol of the tape, which is kind of a special symbol, is not included in this input alphabet. And the constraint is that the tape must be initialized with symbol of the input alphabet initially. Okay, that's just a. Actually, I don't really know why there is this constraint in the formal definition. It's not really that useful, but what it allows you to do is to easily check where is the end of the input, right? Since the blank symbol is not in sigma, you know that if you scan your tape and arrive at a blank symbol, you know that you scan everything there is to scan. Whereas if the blank symbol was inside sigma, you would never know whether you read all the input or not. So you would have to introduce some new conventions, like if you see this character, then stop, and so that would be annoying. So that's the only difference. Then you have gamma, which is essentially just like sigma, but it includes the blank symbol, okay? And gammas are all the symbols that are allowed to appear on the tape. So the machine is allowed to write a blank symbol. There is no problem with that. It just cannot start with blank symbols in the input part initially, okay? So we have the alphabet essentially. And then we have the transition function, very similar to the DFA, but now the transition function is a bit different because it takes as input the current state of the brain, of course, and the current character we are looking at with our control, right? And what it outputs is the new state that we'll be in, the character that we will write at the position where we are, as well as whether we move left or right on the tape, okay? So yeah, the transition function is the same, except it also tells you what to write and where to move. Okay, so good. Then we have, of course, the start state in which we start, and then the halt state, which when we reach it, we just stop applying the transition function. Everything stops, and we can consider that the machine is done computing, right? So yeah, so the halt state, as I said, can also be an accept or reject state if you want to do this recognizing languages, etc. Any questions about this? Okay. So the meat of the machine, kind of the program of the machine, is contained inside the transition functions. That really tells you what to do according to what you receive. Right, so this I explained. And so if you're kind of familiar with these very low-level programming languages, it already starts to look like one of those because you have this reading head, so you point somewhere in memory, and then you choose where to move in memory to read the next thing. So it kind of looks like assembly if you're familiar with that. I'm not actually, but I'm sure some people from computer science are. And so what we did right now is that we've shown that it is at least more powerful than a finite automaton. Okay? Because in particular, you can simulate a finite automaton if you just read the tape one after another and just do the finite automaton stuff. But we know that we can recognize these languages which was not recognizable by a finite automaton. So it's at least more powerful. But how powerful is it? Okay, and this is one of the very beautiful results. It's universality. Okay. We start by noticing that there is a big difference between a Turing machine and a DFA, aside from what we described, is that the DFA always halts. Okay, it always says either accept or reject. Once you reach the end of the string, it says accept or reject. The Turing machine, it can either halt, so accept or reject, but it may just loop forever. Okay, I can very easily make a program that says when you see a 1, go to the right. When you see a blank, go to the left. Okay, if I then feed it with a 1, it will just do that forever, never reach a halting state. And so we have 3 possible outcomes. Either the Turing machine loops, the Turing machine accepts or rejects, which is very different from the DFA. Okay, and this will be very crucial, actually, we'll see. So this is also known as an infinite loop, which you can do very easily in any programming language. Okay, while true, do something, and it's an infinite loop. All right, so to start talking about this, the very nice properties of these Turing machines, we need to be able to talk about them a bit more easily. And we'll do this with the so-called Turing numbering. Okay, so the Turing machine, as we have seen, a specific Turing machine is described by finite amount of data, right? You just tell him what state you have, there is a finite amount. What are the alphabet, there is also a finite amount. And then the transition function, which is also a finite amount of states and a finite amount of alphabets. And that's it, essentially. Okay, so there is a finite amount of data. So what this means is that the number of Turing machines, of different Turing machines, is infinite, of course, but it's a countable infinity. Okay, I can list to you all the Turing machines very easily. I just start with the Turing machine with 1 state and such alphabet, then the Turing machine with 2 states and such alphabets, and so on and so forth. And so what this means is that there is a bijection or a one-to-one correspondence between the possible Turing machines and the natural numbers n. Okay, so the Turing numbering is just a bijection, such a bijection. Okay, what it means is that you give me a Turing machine, and I say, okay, this is Turing machine number 2055. There is a numbering which is 1-to-1. So if I give you a number along with this bijection, you can find which Turing machines it corresponds to. Okay, you just have to imagine each Turing machine can be assigned a unique number, and given the unique number, you can also deduce what Turing machine it belongs to. So this will write it as bracket m. So bracket m is just a number, natural number, which describes the Turing machine m. Okay. So if you want, an easier way to do that would just be that instead of using numbers, you use like text. And so you can have a text that describes the states, the alphabet, and the transition function. And this is uniquely associated to a Turing machine. Here we are just doing it with numbers, so it's kind of more obscure, but it's essentially the same. Right, and one thing to note is that the initial data on the tape is not part of the Turing machine. The Turing machine is just the thing that acts on the tape. But what's on the tape is completely separate from the Turing machine. So now let's introduce some, some definitions, some technical conventions. So the initial data that is on the tape, we will just denote as X, and we consider it to be a string. Okay, that's fine. And we'll see the action of the Turing machine on the string. We will denote it with this symbol, phi. So phi underscore m of X means take the Turing machine associated to m, take the tape with X written on it, and run the Turing machine on this. Okay. And what it does is that the Turing machine will output something. So at some point it will halt. And what's written on the tape when it halts is this thing that I write here, right? This thing. So this thing is a string. What is left on the tape when the Turing machine halts? Is that good for everybody? Any questions? So you have to see it as phi of m of x is just run the machine on x and look at what it outputs. So sometimes we'll just use a notation which is a bit more complete. We write phi m of x, y, if there is a natural separation of the inputs. It's always just one tape, but you could imagine, okay, if you write a Turing machine that sums two numbers, the input is clearly one number and then a second number. In practice, there's just one input, but it might be useful to separate them just for clarity. Okay, so this is the same thing. We just have two inputs which are semantically separate. They mean different things. Right, and then, so here I said that the output of the Turing machine is what is left on the tape. You could also consider a different thing where the output of the Turing machine is either accept if it accepts, reject if it rejects, and loop if it loops. So this, instead of being a string, you could say, okay, I don't care of what is left on the tape. I just care if it accepts or rejects. And so this might be also a function inside this, this set, right? So we'll often use, we won't use this kind of cumbersome notation. We denote the Turing machine itself and the associated number just by a number. Okay, we say, if I say the Turing machine n, it just means the Turing machine denoted by the number n. They mean the same thing. Okay, good. Right, so now let's introduce some theorems, which are very easy theorems, you will see. If you have done a bit of programming, they will be very trivial to you. So we consider a Turing machine n, right? Which takes as input a string w, which is composed of two parts, okay? So just imagine a Turing machine that takes two strings as input, x and y. The SMN theorem, the title is not very nice, okay? SMN theorem states that there is a Turing machine S such that we have this equality. Okay, so let's decorticate this equality. So on the right-hand side, we have the Turing machine N acting on X and Y. All right, that's just the Turing machine we start with. On the left, there is some Turing machine, this one denoted by S of N and X, whatever, that acts only on Y, okay? And the equality here means that they do the same thing, right? The tape is left in the same state at the end of the operation. So what it means is that this Turing machine S of nx, when you run it on Y, does the same thing as the Turing machine N when you run it on xy. So what does it mean? X and Y can be seen as parameters of the Turing machine N. If we look at S and X, this Turing machine takes as parameter only Y, okay? The other parameter X is kind of hard-coded inside the Turing machine. So what the SMN theorems tells us, I will do some examples, is that given a Turing machine that takes two parameters, you can fix one of these parameters to be hard-coded inside the Turing machine. Instead of living on the tape, it lives inside the definition of the Turing machine. So now this new Turing machine does the same thing as the previous one, but you're not allowed to play with X, right? You're not only allowed to play with Y. Okay, so the one way to think about it is that the SMN theorem tells you that you can design a Turing machine that does the same thing as another one, but fixes one of the inputs. And the reason it's called SMN is just that this function is called S, and usually they take as input M and N, and so here you would have SMN, which is very bad. So here it's the SNX theorem, but all right. Okay, so let's make an example to make that clear. So let's consider a Turing machine N+, which takes as input two integers, x, y, and it outputs the sum of the integers. Okay, so f and phi n plus of x and y is x plus y. All right. So if we consider the Turing machine S of n plus 5, it means that we do the same thing as n plus, but we fix x to be 5. We just fix the value of x to be 5. So this Turing machine here accepts a single parameter, y, and it returns 5 plus y. Okay? So in other words, if we write the equation that we have here, we just apply this equation. We have phi of s n plus 5 of y. By definition, by this equation is phi of n plus 5 and y. So it's 5 plus y. So you see this machine here takes only one input as parameter. So the meat of this theorem is that, because here we didn't really state anything, is that this function s that computes, that fixes for you one of these variables, is itself a computable function. So there is a Turing machine that does the job of s. Okay, let me show you an example in Python for this s function. So I don't know how many of you are familiar with Python, but it's the one I'm most familiar with. So we have a function s, right? And it takes as input a program, which I call n, and a variable, which I call x. And what we need to do is output a program that does the same thing as n of xy, but with x fixed. So here is where we define this new program. So this is the new program. So this new program takes only y as input, and it outputs n of xy. But here the x is fixed. So, and then we return this new program. Right. Okay, so what happens? So if I apply s of n5, where n is any program, and then apply this to y, this will be equal to n of 5 and y. So I don't know if this helps people, but kind of think about it. And if you want, you can even like, let's see, yeah. You can even implement this in Python and then go and define like, I don't know, summed of x and y, and this will return x plus y. And then you will see if you define a new program, which is s of summed and 5, this new program, you can feed it like 10, and this will give you 15, right? Because we fixed the first variable x to be 5, and we feed it a y, which is 10, so it gives 15, right? So this is kind of hard to digest the first time. Just think a bit about it, about this equation and what it means. Just in particular, this function s that takes two integers as input returns an integer, right? It returns a new program. So this s of nx, the whole thing, is a Turing machine. Okay, any questions on this? Okay. So here we don't prove this SMN theorem, but the proof essentially goes like, the proof is essentially what we did here in Python, okay? So it's kind of clear that you have a function that takes to argument x plus y. You want to remove one argument and kind of hard code it into the brain of the Turing machine. And you can show that it's something you can do. It's essentially what we do here in Python. Here is a proof of the SMN theorem in Python. But for Turing machines, it's kind of the same. All right, so this is one theorem that we'll need for self-reproduction. And the second one is the universality theorem. And it's sort of the opposite direction of the SMN theorem. So what did the SMN do? Given two input variables, we remove one and we hard code one of those input variables. Here we'll do the opposite. We take something which is not an input variable and make it an input variable. So the universality theorem tells us that there is a special Turing machine U that satisfies the following equation for any Turing machine N. Okay, so let's digest this equation. So you have the Turing machine n that takes x as input. And we say that if you give the Turing machine u, the universal one, if you give him as input n and then x, it will do the same thing. So what this means is that the Turing machine u, you give him another Turing machine n, and it will simulate what this Turing machine does. Right? It will do the same thing as the Turing machine itself. So we call this a universal Turing machine because if you have u, you can simulate any other Turing machine. Right? I can give it here any n that I want, and it will simulate for me the action of the Turing machine itself. Okay, so this is what is here in this text. We give to the Turing machine u a description of another Turing machine n, as well as some input x, and the universal Turing machine compute what the n would compute on x. It simulates n on x. So such a Turing machine u is called a universal Turing machine because given the right input, it can do what any other Turing machine can do. All right? So this, as opposed to the SMN theorem, this seems much harder to do, right? You need a Turing machine that can do what any other Turing machine does. It seems to be very hard, right? Because it has a finite number of states. All the possible number of states for a full Turing machine is an infinite number. So how can it do that? So in Python, it's very easy to do it. Take 3 lines. And the way to do it is this one. And then I'll let you go. So here, this function is a universal function because it can do what any other function does as long as we provide the code of this other function. So for example, what I mean by code here, code would be something like that. Code would be something like def n of x is x squared. Okay? It's a string that contains the code defining any function n. So how do we make this universal function? Or we just take the code and we execute it. Okay, so this means that now we have a function n which is defined inside this u, and then we just apply this function we just defined to x. Okay, so you see that we have the correct property. We have that u of n x, so code for n x is just equal to n of x. Right? And here I can give him the code of any function I can think of. So in a way, you don't need any other function. You just need this one universal function and then the code for the other functions. And that's it. And it's exactly the same for the Turing machine. Once you have the universal Turing machine, you can say, okay, I don't care about any other Turing machine. I will just use this one, just giving the Turing number of the Turing machine that you want to execute. I will plug it in my universal one and I will simulate it. So the proof for this is kind of boring, actually. It's not very nice. So we're not going to go through it. But what it involves is essentially some very boring things. So you just make a Turing machine which can do some set of operations. So it can compare 2 things on a tape. It can mark some things on a tape. It can copy things from a tape. It can replace things on a tape. And you define all these operations and you actually show that you can do them on a Turing machine. And then what the Turing machine does is just that, okay, give me the set of states. Okay, I will write the set of states on the tape. Then give me the transition. I will write it on the tape. And then given an input, it look at what it wrote on the tape and say, okay, I should remove this state and go to this state and do this thing. So essentially, that's how you show that there exists a universal Turing machine. So the proof is not so nice, but it's a very interesting result, okay, that you have this Turing machine that does the job of all other Turing machines. Right. Yes. So for DFAs, I don't think there is a universal DFA that does the job of all other DFAs, but I might be wrong. I'm not sure about that. So let's just finish with the last question, and then you're free to go.
What would be the number of states?
Huh?
What would be the number of states of the DFA?
Yes. Okay. Probably not. Well, it depends.
If it's a
Yeah. No, it
state,
cannot.
then
It
you
probably cannot.
have,
Yes, that's true. So, yes. So the question is, I think I launched it. Yeah. So the question is, what does this do? Okay, where U is the universal Turing machine. Okay, what does this thing do? Right, and so just to say, so for next time we'll look again at this universality, because it's something really unexpected how universal it really is. So we can expect this universality to be like, if we encounter some aliens, you can know that they cannot compute functions that you cannot compute. Like, this is really universal. We'll show this. And then once we have that, we can finally go back to A life and show how this is related to reproduction. Okay. If you're not so interested about this computation stuff, don't worry, it's almost done. Next time, we're going to start looking at reproduction. And we'll see it's actually a very subtle thing. But the good thing is that we'll start to have actually examples, like practical examples. So these questions, yeah, this last question is a bit thought. So many people say that it loops. Some people say it's ill-defined. Some people say that it's a self-reproducing Turing machine. That puts U. So let's take a look. So for me, the correct answer was either it outputs the empty string or it is ill-defined. So it kind of, maybe I'm wrong, but let's see it. So let's unfold this thing. We're just going to apply the equations that we have. Okay, so phi U, U, U. By definition of the universal Turing machine, it does that, right? So it simulates what U would do given U as input, which is exactly that. So here, this, in practice, U takes 2 parameters, but since we just gave it 1, it's just U and an empty parameter. So what does this do? It simulates the Turing machine U on an empty input. So it does this. So here is U with 2 empty parameters. And so here, what does it do? It simulates the empty Turing machine on the empty input. And here you could say, okay, this is the empty input because it does nothing. So here you might complain, you might say, but I chose a Turing numbering where the empty number, like the number 0, is a Turing machine that does some crazy stuff. And okay, you could say that. So it's kind of ill-defined because we don't know the Turing numbering, what does it associate to the empty string, but okay. But you see, so if you are confused about the SMN and the universality theorem, just play around with it a bit. So start with an expression and try to go through the steps. Here, all we did, we did not even think. We just applied this equation repeatedly, right? Just apply this equation. And for the SMN, it's the same thing. All you need to remember is how to apply, how to go from here to here and here to here. And with this, you will be able to prove the existence of self-reproducing programs. All right, great. So see you next week.